Hi, I'm George Hammond, conference producer at Technology Networks, and I'm here to introduce our next talk, Research Paradigms in Materials and Polymers, Modern Tools in the Laboratory. I'm excited to introduce Dr. Rigoberto Advincula, a Governor's Chair Professor at the University of Tennessee and Oak Ridge National Lab. Dr. Advincula is a world-renowned expert in polymer chemistry and nanomaterials and has led groundbreaking research in flow chemistry and additive manufacturing. In recognition of his outstanding work, he has been elected as a Fellow of the National Academy of Inventors, the American Chemical Society, and several of its divisions, as well as the Royal Society of Chemistry. A warm welcome to you, Dr. Advincula. Following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And now, without further ado, I will hand over to Dr. Advincula to begin his presentation.
Well, thank you, George, and thank you, Technology Networks, for this opportunity to give the talk about the modern laboratory and the laboratory leader. And as George mentioned, I will be giving you an overview of what research paradigms we have in materials and polymer research. And then, of course, we will have the opportunity for questions and answers. So, of course, good morning, good afternoon, and good evening to you all. So I'm with the Oak Ridge National Laboratory as a group leader with CNMS, part of the operation with the spallation neutron source. It's actually a $10 billion facility by the U.S. Department of Energy. On the other hand, I'm also a professor at the University of Tennessee. My laboratory is housed at the Institute for Advanced Materials and Manufacturing. So you may say that I'm involved with two laboratories, and such a unique setting or a responsibility gives me an overview on two types of operation and management as well. So here is a picture of my research group at the university. I run a group made up of graduate students, undergrads, postdocs, and visiting scholars. We do a lot of work related to nanomaterials, polymer synthesis, nanostructuring of surfaces, and the use of surface-sensitive analytical tools that we use to probe phenomena. And running such a laboratory means that we have a variety of objectives. Of course, a transformational objective of mine has always been to encourage and to train our future scientific leaders. And thus, the experience they have in a university laboratory setting prepares them for their STEM disciplines in the future. Here we start with a picture of the electromagnetic spectrum. You see, in the human experience, we see, based on the visible spectrum, is what we sometimes perceive as the only reality. But in fact, we are governed by the rest of the electromagnetic spectrum, meaning many things we do not see, including microwave, UV, X-ray, forms part of that human and planetary existence. Also, there are many things we do not see, but they do exist in the nanoscale realm, such that we harness the power of the laboratory, the experimentation we can do, the simulation that we can observe that mimics nature and allows us to construct different types of synthetic technologies that allow us to harness that scale called nanoscience or nanotechnology. Now, let me explain why being part of a group leader means that we have to choose eventually which part of the scientific or technology exercise that we focus on. You see, Niels Bohr is very well known in the area of the atomic theory, of course, a Nobel Prize winner. On the other hand, we know Thomas Edison, a prolific inventor, founder of the General Electric Company, and he is famous for saying that invention is basically 1% inspiration and 99% perspiration. On the other hand, we sometimes forget that there's another type of scientist. His name is Louis Pasteur. We drink milk. We use a process called pasteurization or pasteurized milk. We measure things in the laboratory using a pasture pipette. If you're an organic chemist, certainly you will be familiar with these contributions in stereochemistry. Yet Pasteur is a scientist that embodies accomplishments, high accomplishments in the fundamental science, yet is very prolific and very um, targeted in contributing to society by producing practical things. So this is, by the way, called the Pasteur's quadrant. And at one point, as a scientist, you will end up doing or categorizing yourself in any of these three uh, categories. And in fact, I classify myself these days as more of the pasture type of scientist. And why not? The science of today eventually becomes the technology of tomorrow. And therefore, many things we do in the laboratory will bear its fruit in a society through translational research. Now, let me describe first the type of materials we have. Material science thrives on the study, phenomena, and harnessing of materials. The three major classes that include polymers, metals, ceramics, and of course, there are various subclasses of metals, polymers, and ceramics. Polymers can be classified as thermosets, thermoplastics, or elastomers. Metals can be configured as ferrous or non-ferrous metals. When it comes to polymers, we call them plastic, more familiar term in society. They are used for packaging, for bottling, coatings, packaging, textile, yet many of the things associated with plastics are often bad in terms of how society misuses them. And in fact, recycling versus upcycling means there's always the objective to do work that improves their high value proposition, either as new chemical intermediates, repurposing them, or using a more efficient process to produce or upcycle these materials. Polymers are actually large molecules, and we sometimes call them macromolecules. The way they are synthesized or made as blocks or different type of microstructures, architectures means that harnessing the structure, composition, processing property of these materials is very important for their ultimate use. And this is actually the expertise we have in our laboratory, both at the university and at Oak Ridge National Lab. Now, bridging science towards innovation or translational research means that we have to use engineering on the science or applied science. That is, we take the best of the basic research platform, and then to translate them to the market, we need to understand the needs and the value proposition of the market. And very often, when you offer a solution to a problem that somebody is willing to pay for, they're looking for an increase in efficiency or performance cost ratio. So if you simply target a solution without a problem, then you will go nowhere. On the other hand, if you understand the problem and try to find a solution through value proposition, then you will be a winner. Here we can see that various types of laboratory operations within industry or academia or government or even SMEs, small businesses, means that they're always looking for a uh, technology breakthrough that allows them to get the real value by allocating resources that allow them to advance. So, for example, in academia, we're always interested in getting the best research output for a publication. In industry, they're interested with the economics and profitability of the operation. In the government, of course, like the Oak Ridge National Laboratory, we're interested in conducting science with a specific mission, let's say, of the Department of Energy to make more energy efficient devices, processes, and materials. So everybody's talking about Industry 4.0, and of course, the digitalization of manufacturing and the economy means that we are getting more reliable towards data or computational methods or focusing on efficiencies and even sustainability. 3D printing is a very important uh, technology that allows us to uh, go towards digital economy, where we can use the, let's say, computing power or simulation, including AI and machine learning, to improve the optimization of materials or design. In fact, I will be explaining a little more about AI and its impact on the laboratory of the future. And as a laboratory leader, increasingly AI will become a tool that will make your operation more efficient, if not equip your staff or your students towards a new tool or better tool for doing science. So why an R&D laboratory or why set up a laboratory? Of course, people have can divide the word laboratory into labor, okay? Meaning there is work directed towards doing research, product development, solving challenging problems, or we simply use laboratory for testing. But for me, an important aspect of a laboratory is for training, for building relationships and alliances. And for a company, this can be important for developing new products for R&D that can generate more revenue for the company or even intellectual property. So essentially, the laboratory is a workplace, a training ground to conduct scientific research or to do testing. Is actually an ecosystem for creativity that will lead to intellectual property or scholarly output in terms of publication. It is key towards uh, improving the way we do things, the way we operate things, or in a way, this is a innovation ground or operation that allows us to build up more technology. Now, many attributes that I can see as desirable in running a laboratory means that this is a um, place where we can engage and collaborate using research resources or tools that allow us to come up with products and creative solutions. It is an engine for disruptive breakthroughs or the discovery of phenomena or even Nobel Prize work in the future. It is a place where one can create patents, very powerful tools for a company for protecting its intellectual capital or creating various IPs that can be licensed. It is a place where we can develop core technologies or procedures that can be used to improve the methods that are uh, past and modernize them towards higher efficiencies. Place for testing using international standards such as the ASTM and ISO. It is a place for investment. One can see this as part of the capitalization for a company. It's a place where teams, research groups can be built up towards targeted objectives and investments. Now, the development of an ecosystem where we can have disruptive new technologies and then even converted into products in record time. So there are many desirable attributes in running a laboratory. However, paramount to a laboratory is safety, and this is sometimes taken for granted. But safety is phenomena because we are looking at safety towards our staff members, students, ability to use tools, foods, instruments properly. In the case of biocontainment, safety, radiation safety, lots of trainings are involved, and even a regular safety audit is important. Sustainability means we sometimes look at running a laboratory to be efficient, cost savings, both in energy, running the building efficiently, automated systems to enable us to save cost. So I'm going to go back and forth explaining some of our philosophy in running a laboratory, as well as what it means to be a place for innovation. You see, innovation means not only that we do translational work, but we actually use it for training and also an output that is desirable for commercialization. So an innovation ecosystem means that we want to have an environment that fosters creativity with a specific direction that benefits both the researchers and the organization. Meaning that in using technology, we want to develop an ecosystem that allows us to develop this IP for the market in specific stages, whereas when what we call R&D could result in improved processes or product development. Again, as I said, R&D is also a place where we can train capital resources based on the human resource. So what I mean by that is a most important role for the laboratory is training the professional, the future professional. And that means it entails working with master's and PhD students or training the future graduate students through an environment that will allow them to experience creativity in a safe environment and targeted mentoring. And actually, in my laboratory experience, especially as a professor, we have mentored many PhD students, undergrads, visiting scholars, and even high school students. And this is really part of running a modern laboratory in an academic setting. Part of this is I teach my group members to have critical thinking skills that allow them to focus or observe phenomena, develop algorithms or methods of answering hypothesis questions that can be answered by doing the experiment in an empirical basis, drawing out conclusions that can be used to answer these questions, and maybe even developing a feedback loop that allows them to have continuous improvement and focus, let's say, on getting enough papers for their dissertation. So part of this in training the young mind of a scientist in a laboratory is to give them skills, soft skills, hard skills, hands-on research skills, manipulation of instruments. And this can be done even in a collaborative community where they work with other undergrads, graduate students, and postdocs. And sometimes we even inject entrepreneurship and innovation skills. After all, innovation is really people creating value by implementing new ideas and translating it towards a particular product or direction, even in an interdisciplinary setting. So part of my responsibility now with Oak Ridge National Laboratory is that I'm a group leader of the CNMS, the Macromolecular Nanomaterials Group. We focus on synthesis of polymers, deuterated material, probe materials, development of techniques, state-of-the-art characterization methods, simulation. And in fact, when I joined the national lab, I introduced and developed two laboratory um, capabilities. One that involves 3D printing with 5, 6 different 3D printing methods, and a laboratory that's focused on machine learning directed synthesis. CNMS actually has a unique and dual nanoscience mission in that we do science, but we also work with users, or we serve the community by being a user facility. And in this case, we collaborate with these users or collaborators in using the state-of-the-art equipment or synthetic methods to accomplish science or even do translational research. Thus, our laboratories are very well equipped. We have many tools for characterization of polymers, small molecules, including X-ray, NMR, GPC, thin film characterization methods, rheology, and dielectric property measurements. Then, as I mentioned earlier, we have developed two capabilities based on 3D printing techniques as well as continuous flow reaction chemistry through machine learning directed synthesis. Now, a little more about our research. So nanoscience, nanotechnology means that we can harness properties of uh, materials at the nanoscale. And in fact, nanomaterials are even commercially available, whether it's carbon nanotubes, graphene, nanoclay, and so on. So polymers can be observed within the scale based on their grafting as polymer brushes or a controlled aggregation that results in interesting colloidal phenomena. Yet their scale is similar to what we would observe with quantum dots, graphene, silicon nanoparticle, and so on. So they are true nanomaterials. And we've been busy in many ways, which includes the synthesis of polymers that have electro-optically active properties, polymers with controlled entanglement through supramolecular knotted templates, polymers that can be grafted on surfaces using surface-initiated polymerization, and the layer by layer adsorption of polyelectrolytes towards controlled nanostructuring and even formation of hollow shell structures. We've even been involved with the synthesis of dendrimers or hybrid nanoparticle dendrimers that can have interesting charge and electron transfer properties. Now, in 2016, our laboratory turned into more interesting aspects of manufacturing, in that we were interested in using polymer materials for digital manufacturing, bio-inspired design, inner space, outer space manufacturing, so on. And this was actually a collage of images coming from my talk at the World Economic Forum back in 2016. In fact, 3D printing goes towards the fabrication of parts, objects, construction of um, uh, parts or OEMs used in the automotive, aerospace, marine industries. In fact, the first 3D printed sports car with a 1964 design was actually done at Oak Ridge National Lab. And 3D printing really goes into many, many applications, including electronics, consumer devices, medical devices, and so on. I mean, if you look at this picture here, you can even have a 3D printed Jeep, which was last made during World War II. So you can see here the importance of 3D printing. And in fact, in our laboratory, we have 3D printing capabilities of various techniques that allows us to produce and observe nanomaterials and nanocomposites towards manufacturing. So in this case, 3D printing has the advantage of being more useful when the object is more complex or has a higher performance. So we've been busy in our laboratory doing investigation of polymer nanocomposites as they are applied to 3D printing, and that includes characterization of their properties and reporting their phenomena. So one paper that we recently produced is quite different from our previous work. You see 3D printing of PVDF or polyvinylidene fluoride with epoxy materials such as molybdenum sulfide, we were able to do this project in record time. And eventually, what we observed was a quadrupling of the piezoelectric effect. Now, the reason this is so different is that we actually applied machine learning. And in this case, finite element analysis with abacus learning enable us to actually predict the properties and optimize their preparation based on simulation and specific algorithms that allow us to observe the efficient distribution of the nanomaterial, including predicting some of the properties of their rheology. And so we were able to work this project in record time in collaboration with the University of North Texas. And this is all because we applied AI or machine learning. Which brings me to an important point. The modern laboratory today will make use of AI and machine learning to improve their methods of doing research, if not accelerate the discovery process. So actually, machine learning is a more useful term. It's a subset of the artificial intelligence or AI movement. Deep learning comes when we apply generative learning to improve the algorithms of our phenomena or explaining our phenomena or even designing our network. So in this case, a very important step is to produce digital twins. And often this can involve simulation from the quantum chemistry level all the way to the process engineering level. And we sometimes have to build up large language models to come up with data or even simulated data. Now, critical to all of this is actually doing the work. So in a laboratory setting, you will have first to design a workflow where you can take the initial training data set, the algorithm that was probably improved using neural networks, and then doing the experiment itself. You get the result, you evaluate it, and then you compare it to the previous data, improve on it, and come up with an iterative cycle that allows you to end up with an optimized model or result. So this machine learning workflow is going to be increasingly used in our laboratories and even expanding towards manufacturing. So in this last example, before we go to the Q&A, I will describe to you how we have transformed our laboratory into using flow chemistry synthesis. So being a laboratory leader means that we have to be adept towards the latest, if not the more important tools available for us. And in this case, at Oak Ridge National Lab, we were interested in answering the question, can we run an autonomous laboratory with minimum human intervention? So to do this, reach this goal, the chemistry laboratory in the future will increasingly use flow chemistry. I believe this is the case because we can bring more engineering into the chemistry by converting it into a unit operation. And we have been working on flow chemistry synthesis for a while. And this can be used for synthesizing polymers, crafting polymers, or even making nanoparticles. So, in the future, is it possible for us to use machine learning or machine learning directed synthesis through the use of laboratory tools that includes monitoring or sensing, or even having an edge server that collects both the data and controls the experimental station, and then finally access to a high computing facility that allows us to do real-time algorithm development. So this laboratory of the future will mean that we basically have a computer that controls the dosing of the reactants, a tube reactor or a coil reactor that can be operated as a plug flow or a packed bed column. And then we will have analytical tools that monitor the reaction in time or space series, even producing two-dimensional, three-dimensional plots that allow us to do correlational and causational conclusions on our results. So that means that we need to connect various instruments into this system. Quite challenging, in fact, that you have to do different types of interfacing or develop APIs that allow these instruments to communicate. And it turns out that it's even faster or better if we make our own instruments rather than taking commercial instruments and converting them as monitoring instruments for the flow. So as an example, we focus on the synthesis of a copolymer that involves two monomers rather, and an initiator controlling the temperature, the pressure, the flow rate, and thus produce gradient polymers that can be designed initially with the workflow that takes advantage of various combinations of parameters that can be give us the best conclusion. In other words, we can do this experiment by first simulating or creating a digital twin, doing the experiment on a flow chemistry setup, monitoring the reaction as a time or space series. So in this case, the NMR, the IR, or the UVV spectra, and then finally running the instrument in a feedback loop operation to optimize the result. We've been busy trying to develop this laboratory of the future. And I, as a laboratory leader, basically brings many components into this orchestra, leading towards a autonomous operating laboratory. So I hope this has given you a picture of what it is to run a modern lab, both in a university or a national laboratory setting. And with that, I'd like to thank you and be happy to take any questions.
Thank you so much, Dr. Advincula, for that fantastic presentation. Your talk about the human element in modern labs was truly fascinating. As mentioned, we do have a couple of minutes to address some fantastic questions raised from our audience, so let's jump right in with your first question. Firstly, fostering creativity and collaboration is crucial for successful research. Beyond providing advanced tools and resources, what other strategies can laboratory leaders implement to foster creativity and collaboration among their staff, particularly when working on complex material research projects?
Mhm. Yeah, very good question, George, to start the QA. Uh, Very often, I come up with ideas, I read papers, and share it to the team. That in turn helps them get literature or stimulate their thinking. But communication is the key. So as often as you communicate these ideas and get a feedback or both ways, hear from their results or actual work in the lab, following up on leads where the phenomena was unexpected. It's actually more exciting and interesting. Uh, we can do uh, work on directions that are new and allow us to foster creativity in our work, again, by implementing tools like AI and machine learning. So the overall experience here really is communication. Communicate, and the more you discuss things among yourselves, the better that creativity goes.
That's fantastic. Thank you so much, Rigoberto. And moving on now, from a leadership standpoint, how can you ensure that researchers have the necessary skills and trainings to utilize both advanced experimental techniques, such as neutron scattering and AI and machine learning tools, for a well-rounded research approach?
Hmm. Yes, that question really fits to our operation at Oak Ridge National Lab. You see, the group I lead, called the Macromolecular Nanomaterials Group, is one out of seven that actually interfaces with neutron scattering experiments done at the Spallation neutron source. And a lot of our planning involves trying to incorporate neutron scattering as a key technique for investigating phenomena. And again, communication means we have our regular group meetings that we do twice a week. We share publications. I form clusters of teams of staff and graduate students to work on a particular direction. where it makes sense in terms of their skills and interests. So, for example, I would form clusters of students and staff who are very interested in the investigation of polyelectrolytes with specific interests on their solution phenomena, aggregation, and charge pairing. Another group that we would focus on is that I would form a group or a subgroup of staff and students who are interested in 3D printing of these polyelectrolyte complexes. So you can provide leadership that way by directing them in a certain uh, leaning towards the science itself or directionally forming groups that allow them to work together.
That's another fantastic answer. Thank you so much. And speaking of navigating this new landscape, there's a lot of focus on automation. But how do you, as a leader, strike a balance between allocating resources for these cutting edge technologies while still recognizing the importance of human expertise in the lab?
Yes, I like that question simply because this is a, a lean on why we are doing automation. So, for example, the last project I showed on flow chemistry means that we can essentially run this instrument 24/7 and even remotely control the experiment if we have the proper interfacing. So automation and the use of machine learning, AI tools only make sense when we develop this experimental station that allows us to monitor the results of a reaction both kinetically and thermodynamically, and at the same time control the experiment based on dosing or control of their environment, such as the pressure, volume, and temperature. Now, actually, it does take a lot of work. That means that I brought experts in the area of Python programming, in the area of interfacing the instruments with the flow chemistry setup, and even bringing the real chemists who can design the experiment with the idea that we can optimize it based on the parameters that we introduce. So overall, automation is a key step towards improving the efficiency and perhaps bringing more creativity. And I like to use the term bringing more engineering to the science because engineering means we can be mindful of parameter or parameter control that allow us to do the science more efficiently.
Wonderful. Thank you so much for clarifying that for our audience. Now, we have time for just a few more questions today before we close out this session. So, shifting gears slightly, funding is always a challenge, especially with new advancements. In a competitive research environment, how can leaders secure funding and resources to support both the development of in-house AI/machine learning tools and the training of staff to utilize them effectively?
Hmm. Yeah, again, that's a very interesting question that dichotomizes what we have and can do in a national laboratory setting compared to an academic setting. So, in a national laboratory setting, by design or mission, we do science. We don't do as much teaching, although we do a bit of mentoring every summer. A lot of the laboratory resources can come from internal funding or external funding with the Department of Energy, and they're all designed on particular themes and capabilities. So, for example, this autoflow setup was part of an internal initiative to develop the laboratory of the future. On the other hand, in academic setting, you can be very successful as well. But this means also competing with grants, writing grants with the National Science Foundation, the Department of Energy, the Department of Defense, and you can write very competitive ideas and proposals, competing with the rest of the other schools. But in the end, the best ideas win. So whether you get the funding or not, somebody will get the funding simply because they have the best ideas. And yeah, indeed, it is challenging at times, but if you don't write the proposal, if you don't do the step to put your ideas into a competitive format, then it's not It's not possible to do research without that funding.
That's fantastic. Thank you so much. I am aware of the time that we have left for the session, and it looks like we just about have time for one final question today. So, as a leader implementing new technologies like AI and machine learning, how do you establish metrics to evaluate the success of these tools in your lab, ensuring that they are driving scientific progress rather than simply automating tasks?
Yes. So AI and machine learning is, I hope it doesn't become a cliche. I believe it will not. Simply because, yeah, we have to look at it as a tool. A tool means you have to know how to use it and use it wisely, use it appropriately. Machine learning is probably a more appropriate term because whenever we do experiments, we design the experiments, we use statistics, probabilistic techniques, we develop algorithms or equations on hypotheses that we want to answer. So, in essence, everybody's actually been doing a bit of machine learning. So by directing AI machine learning in a more targeted way towards optimization. So optimization means increasing the yield or reducing the amount of energy to do the reaction, or simply developing a faster protocol to do all those tests and characterization means that we have to use it in order to accelerate the way we do things. And I believe the human in the loop is not going to go away, at least anytime soon, because a lot of these things are hard to simulate. And truly, a skilled person in their own science or engineering domain will go a long, long way whenever they use AI and ML. And so that means if you don't want to be obsolete, be the best scientist or engineer that you can be.
Thank you so much, Dr. Advincula. Unfortunately, that is all that we have time for today. But a massive thank you once again to Dr. Advincula for sharing his expertise, and we really do appreciate your time. However, if any of your questions weren't answered today, don't worry. We'll be sure to send all unanswered questions to the speaker after the event. And remember, just like all the other talks, this session will be available to watch on demand for the next 30 days. Thank you once again to Dr. Rigoberto Advincula, and we'll be right back with the next talk.
Thank you, George, and Technology Networks.